Hello, Calc students. It's time to dive into a few differential equation application problems. Many of them are titled here, and we'll do the first problem right here. It looks like this. It doesn't really have a context, but I think what this piece is you'll see in a moment or in a few problems is that we've got some change in some variable or effect over time, and it looks like here you're getting 1/2 of what is already there, and then at per unit time 250 milligrams, liters, whatever is leaving. So this first one is just to kind of find the general solution. So we have been doing a lot of work on separable differential equations. So that's what we do. We separate between y and x, or y and t here. And so step number 1 to separate is I'm going to have 1 over 0.5y minus 250 dy equals dt, or 1 dt. Now in a few minutes I'm going to show you what I think is a little bit easier method to do, but for right now this is how we've done it. We've separated, and we haven't really manipulated any of the initial pieces to make it easier on us. Okay, after we separate, we place an integral sign, or the s, in front of both sides. We can integrate on both sides. That's just an operation. And that becomes, that means that's a function inside a function. So we're going to have to do a little mini u sub. And if you can get to this before, without doing a lot of all the steps, I totally get it, but I'm going to, for the first time, say that, pretend like we're going to do it as if we don't know what's happening. I'm going to call it 1/2. U is 1/2 y minus 250. We do the inside piece. Du is 1/2 dy. So dy is 2 du. So that integral then, I'm just going to continue the side work. This is the mini u sub work here. That means our integral is going to be 2, and it's the integral of 1 over u du. That's what u sub does. It makes something very much easier to integrate. So that means we're going to have 2 natural log of 1/2 y minus 250. All right, I'm going to do the p and then the a. That's the antiderivative on the left side, because we've got everything ready to make it 2 natural log of 1/2 y minus 250. It should be an absolute value. Equals, on the right side, that's just t plus c. I'm going to take the c's and kind of gather them over on the right. Okay, I'm going to change this. This is meant to be, it's supposed to be an absolute value. I'll tell you why we can separate those, or we can take them out in a moment. All right, let's divide by 2, so that means natural log of 1/2 y minus 250 equals t over 2 plus, now this is just c over 2. I'm just going to keep it c. We're still in general land. We can keep that c a constant. We haven't invoked any initial condition yet. And so then I'm going to take both sides as exponents with e as a base. So that liberates the natural log. I should have 1/2 y minus 250. And here I can take out the absolute value, because I think e is always going to be positive. I believe that's why I can say that. So that's 1/2 y minus 250 equals e to the t over 2 plus c. Now, a standard trick or standard move for us calculus students is e to the t squared plus c can be written as that same base but multiplied, so it's e to the t over 2 times e to the c. And this e to the c is just a constant, so we're just going to write it as, left side stays the same, c, e to the t over 2. Many teachers might write a or something else, but that is just a constant. Now we keep going. Now that's the easy part. So that means 1/2 y equals c e to the t over 2 plus 250. We multiply by 2, y equals, again, that's going to be, we can keep it as a c, e to the t over 2, but the 250 needs to be doubled. That is a specific number, 500. I'm going to box that around to know that that is our general equation, general solution to this differential equation. Okay, if you're still with us, I'm going to show you a nice little, like what I call the factor method to make things easier from the beginning. Let's call this, I'm going to put it right down here and call it the factor method. Same problem is, let's see, dy equals, instead of, let's see, 0.5y minus 250, I'm just going to, let's see, dt. I'll start from scratch there. Let's write this as dy dt equals, I'm going to factor out a 1/2 or a 0.5. And that means I have y minus 250 divided by 1/2 is like 250 times 2, that's 500. It helps to sometimes factor out that multiplier in front of y so that you don't have to contend with a little mini u sub. Now we keep going, and that becomes, let's see, I'll separate variables. That means it's 1 over y minus 500 dy equals 1/2 dt. The separation part has happened. We do the p, which is the place an integral sign on both sides. And now this part on the left, it is a mini u sub, but the coefficient of y is just 1. We just have to worry about the natural log of y minus 500 equals, on the right side, 1/2 dt. That is just t over 2 plus c. So the s, the p, and the antiderive has finished. Now, let's see, we're going to solve for y. That's e as a base, both sides. That's y minus 500 equals e to the t over 2 plus c, which I can do that trick again to take e to the c power. So that's, I'll do it in one step. Y equals c, e to the t over 2 plus 500. It's a little bit easier if you do the work ahead of time and factor out that multiplier to help you. Okay, those should agree, yes. Now, the second part of this problem has it's the application kind of piece. Sketch the graphs of several solutions to this differential equation using different initial values for y. This is a little bit of a departure from what we've normally done. Usually you get what is the initial condition, but this time you try different initial conditions or initial values. And what that means is you can kind of think, okay, what if y0 was 400? What if y0 was 500? What if y initial condition 0 was 600? Here's what's going to happen. And I graphed this on Desmos to kind of see, and I chose these numbers strategically because 500 is special. That becomes what's called the kind of the equilibrium value, that if 500 is your initial condition, then your equation is like a steady state. it stays where it is. If you have something lower, if your initial condition is 400, and this could be like milligrams or liters or whatever, it looks as if that starts to degrade. That's y equals 500 minus 100 e to the t over 2. Why do you say that? When we put in a 400, you'll find, if you find the initial condition, you will get that constant to be negative 100. On the other hand, if you put in an initial condition something like 600, you'll find that that c to be something larger, which means this function grows a little more than the equilibrium. And that means that's going to be y equals 500 plus 100 e to the t over 2. Now this magic part here where you get the 100 and minus 100, you've got to do the I and the C part in our acronym to find out what that constant is. And this is where the application of things is going to go. These different, we're going to have marshmallows that are cooling and things that are growing, drugs in the body that release a certain amount each time, and then the body subsumes part of that. Those are all differential equations that can be modeled with things like this. All right.